This is our last video on systems, and in this video we are going to look at systems of non-linear equations. So I have 3 examples that we're going to look at here already. The first one, we're going to use graphing. So we'll look at a graph to determine what's going on here, and then the other 2 we'll solve algebraically. So what I want you to remember is that we use graphs with linear systems before. So when we have systems of linear equations, those are represented by lines, right? So when we're looking for the solution, we're looking for the point of intersection of 2 lines. And of course, as we discussed in our video on 2x2 systems, lines can be parallel, 2 equations can be equivalent, so that can lead to different things that we see on the graph. In the case of nonlinear equations, the graphs are not going to be lines. They could be all sorts of things. Parabolas, they could be polynomials. They don't even have to be functions, right? So these are just equations. There's nothing saying that they have to be functions. So I went ahead and I put the 2 equations that we have here into Desmos so we can look at the graphs. So the first equation, we have x squared plus y equals 0. The second equation, we have x cubed minus 2x minus y equals 0. So let's go ahead and pull up Desmos. So x squared plus y equals 0. We have a parabola, right? So x squared plus y equals 0 here. So, you could probably have seen that coming, since you could have rewritten that as y equals negative x squared. But we don't need to put that into Desmos. If we just write an equation into Desmos of 2 variables, Desmos will graph it. And then for our second equation, x cubed minus 2x minus y equals 0, similarly, you could have probably analyzed this a bit going in, and you could have seen that this is a 3rd degree polynomial, so we're not terribly surprised by the graph. All the same, when we look at the 2 graphs, what we see is that they cross in 2 places. And the nice thing is that if you tap on the graph, so here I am not tapping on either graph, if you tap on either one of the graphs, the points of intersection are going to be highlighted. And I just misspoke. I said that the graphs cross in 2 places. They actually cross in 3. So here is the first place where they cross. So the first point of intersection is -2, -4. Here is the second point of intersection. It's the origin. And here is the third point of intersection, 1, -1. So this system has 3 solutions, -2, -4, 0, 0, and 1, -1. This is the big distinction between linear and nonlinear systems. With linear systems, either the system has 1 solution, or infinitely many solutions, or none at all. So the only finite number of solutions that it can have is 1. With nonlinear systems, there are infinitely many possibilities. You could have 1 solution, 2, 3, 4. So it will completely depend on the equations at hand. So let's go ahead and write that down to kind of finish up this first example. So the solutions are -2, -4, 0, 0, and 1, -1. Let's double check to make sure that's correct. And yes, it is. What I am not going to do here, but that I encourage you to do on your own, is check that these three are all in fact solutions. So these are systems of equations. So the fundamental concepts behind them remain the same as they were before. A solution is only a solution if it satisfies all of the equations in the system. So it's not a bad idea to take the time to check that all three of these points satisfy both of these equations. These two systems we're going to solve algebraically, but I encourage you, after we're finished with that, to put the equations into Desmos and to confirm that the solutions we get are in fact A, the correct solutions, B, the only solutions. So never forget that you have that graphical option when you have systems of equations in two variables, because Desmos will graph any equation in two variables for you. Just like with linear systems, we essentially rely on two methods. We have the method of elimination and the method of substitution. So what I'm going to do with the two examples we have here, one of them I'm going to solve using elimination, the other one I'm going to solve using substitution. Just like before, I'm going to go ahead and number my two equations, equation 1 and 2, and I'm going to lay out a plan. So you can see that in my top equation, I have negative y squared, and in my bottom equation, I have plus 4y squared. So a nice clean way to eliminate here is to eliminate the y's. So I'm going to go ahead and take the first equation and multiply it by 4. And add it to the second equation. So that gets me 12x squared minus 4y squared is equal to 44. And then here I have x squared plus 4y squared is equal to 8. Adding these two equations together, I have 13x squared is equal to 52. Notice that the y terms eliminate. From here, I'll divide both sides by 13, so x squared is 4. And if x squared is 4, then x is either positive or negative 2. Okay, so let's see what y is. Well, we can use either one of our equations. So let's look at the second equation to find y. The reason I'm looking at the second equation rather than the first is mostly random, but partly because in the second equation, x squared is by itself, so it might be a little bit easier to manipulate and to work with that equation. Okay, so remember, x can be either 2 or negative 2, so we're going to look at both situations. So if x is 2, then I have x squared is 4 plus 4y squared is equal to 8. So I have 4y squared is equal to 4. Y squared is equal to 1. So y is either plus or minus 1. Okay, so I have two possible solutions here, so let's check to see if either one of them or both of them end up working. So check 2, 1. Okay, so checking 2, 1 in the first equation, I have 3 times 2 squared, which is 4, minus y squared, which is just 1, and that is in fact equal to 11. And then for the second equation, I have x squared, which is 4, plus 4 times y squared, which is just 1, and that is in fact equal to 8. And you can see pretty quickly that 2, negative 1 will work in the same way, okay? So 2, negative 1, I will let you check on your own, but 2, negative 1 also works out. since when you square -1, you get the same thing as when you square 1. Now, notice this was us going through the process of solving for when x was +2. But we also have the possibility of looking at when x is -2. And I'm not going to go through the whole process of doing what I did here, just because you will see very quickly that if I plug -2 into the second equation, it's going to look exactly the same way. I'm going to have y squared is equal to 1, so y is either positive or -1. So what this tells me is that I have two more solutions, -2, +1, and -2, -1. So this is an example of a linear system that actually has 4 solutions. I think I might have said linear systems, I meant nonlinear system. So let's see what this looks like graphically. Okay, so we have 2 equations. Let's go ahead and put them into Desmos. So our first equation is 3x squared minus y squared is equal to 11. Okay, so I'm going to go ahead and remove out the other 2 equations so they're not convoluting things here. And then my second equation is x squared plus 4y squared is equal to 8. So there they are. One of my equations is kind of this oval graph, and the other one is this kind of double lobe graph. Those are actually called conic sections, and we're covering them next week. And there they are, my 4 solutions. 2, 1, -2, 1, -2, -1, and 2, -1. Never forget, Desmos will graph any 2-variable equation for you. Use that. Check to make sure that the solutions that you think work actually show up on the graph. Okay, and now for the third and final example in this video. I said that we would use the elimination method for the first and the substitution method for the second. So here, numbering my 2 equations 1 and 2, I'm going to use my first equation that has x by itself to solve for x. So x is 2y plus 2. And now I'm going to take that and substitute it in to the second equation. So I have, everywhere that I have an x, I'm going to replace it with 2y plus 2. So I have y squared minus 2y plus 2 squared is equal to 2 times 2y plus 2 plus 4. So I'm going to go ahead and open up some parentheses and combine some like terms. So I have here y squared minus 4y squared minus 8y minus 4. And that's equal to 4y plus 4 plus 4. Okay, so on the left I have negative 3y squared minus 8y minus 4, and that's equal to 4y plus 8. So this is a quadratic equation. I can solve it. So I'm going to achieve that by moving everything from one side to the other side to set it to 0. You'll notice that everything here on the left is negative. So to avoid having to deal with negatives, I'm going to go ahead and add everything on the left-hand side over to the right-hand side, setting my left side to 0. So I have 0 is equal to 3y squared plus 12y plus 12. So conveniently, what you'll notice here is that everything is divisible through by 3. So that'll help me a lot with factoring and seeing the solutions, because it'll make it so that my leading coefficient is 1. So I'm dividing both sides by 3, and that gets me y squared plus 4y plus 4 is equal to 0. This is great. The right-hand side is just y plus 2, quantity squared. And that's only equal to 0 when y is negative 2. So y equals negative 2 is the only possible way that this is going to work. And I have this expression here that says that x is 2y plus 2. So that's 2 times negative 2 plus 2, which is negative 4 plus 2, which is negative 2. So according to what I'm seeing here, this system only has one solution, and it is negative 2 comma negative 2. Let's go over to Desmos. I've actually gone ahead and put in those two equations that we were just working with, x minus 2y equals 2. So that is a line. And y squared minus x squared equals 2x plus 4. So when we tap on one of these equations, we see, sure enough, that these two only have one point in common. And there it is, the point negative 2 comma negative 2. So this is the essence of nonlinear systems. The concept is the same. You have two equations, and both of them have to be satisfied in order for a pair to be a solution. However, because they are nonlinear, graphically speaking, you are no longer looking for the intersection of two lines. You are now looking for the intersection of two graphs. They could be lines, they could be curves, which means that you are no longer required to only have one solution. You could have multiple solutions, right? So in our first example, we had 3 solutions. In our second example, we had 4 solutions, and in our last example, we only had 1. So taking the linear requirement off the table greatly increases the number of options that you'll see in terms of the way things look and the solutions. So really use Desmos to make sure that your solutions actually line up with what you see on the graph. This concludes our video lessons on systems and the lessons for this week.